Now it's not exactly the problem from your homework. So here's my phase plot. I've got my differential equation. I've got all of the equilibria. And now I want to know the fate of the world if we start with different numbers of foxes. And I'm going to figure that out by using those same tricks we were working on last week, thinking about this curve everywhere above the axis that's telling me that f prime is positive, which means f is increasing, and the larger values of f are to the right. Everywhere down here on the curve, my f prime is negative, which means f is decreasing, which means we are moving to the left. So if I pick a starting number of foxes like 2, then I would look to the curve, because the curve when f equals 2 is above the axis, I'd say, oh, hey, f prime is greater than 0, so f is increasing, so we move to the right. So for any number of foxes that live in here, all of those I am tending toward the right, towards increasing values. Now, if I think out here, the same thing's happening. So everywhere on this curve, we're above the axis. So out here, we are headed to the right. Everywhere else on the graph, my curve is below the axis, which means I would be headed to the left. Now that makes kind of an interesting thing happen over here at 5 zombie foxes. So this isn't a thing that our textbook talks about, but this would, well, not in this section, this would still be considered unstable, because a slight perturbation, meaning if I move off of that equilibrium a little bit in one direction, I do head away from the -5. In some textbooks, we call this semi-stable, right? Because from one side we're stable, so half from one side we're stable, and sort of from the other side we're unstable. So based on this picture and this phase plane, we would be able to know how many foxes we would end up long-term for different starting values. For example, if my starting number of foxes is equal to 2, then that limit as t approaches infinity of the number of foxes, so long-term behavior. So if we start with 2 foxes, that means we start in here, and the long-term behavior pushes us towards 3 foxes. So my limit as t approaches infinity, this would be headed to 3. If I started with 5 foxes, then looking at the graph, 5 is right here. 5 is already in equilibrium, which means if I start with 5 foxes, my f prime, or the change in the number of foxes, is 0. So we're going to stay at 5 forever. I wrote that weird notationally. If I were to start with 5 foxes when t equals 0, then that limit as t approaches infinity of f would be equal to 5. So depending on the starting number of foxes, that limit as t approaches infinity is going to be different. I figure, because I know nothing about unicorns, I should be able to choose anything, and maybe the negative numbers make sense. Maybe weird things make sense. So what if my change in unicorns over time is governed by the equation u minus 3 divided by u plus 9. So first thing I'm going to do is look at that equation and say, I guess I should ask us a question first, but I would like to find and classify any of the equilibria. Well, if I set this equal to 0, and then we use our 17A skills or pre-calc skills, the only way that my fraction can be equal to 0 is if the numerator is equal to 0, which means u equals 3 is the only equilibrium. Something interesting might be happening when u is equal to -9, but it's not an equilibrium value because it wouldn't make our derivative go to 0. The next thing I want to do is to sketch the phase plane. So I need to sketch this function. Now I'm really using my 17A skills here, or pre-calc skills. I know that there's a vertical asymptote at -9. And I know there's a horizontal asymptote at 1. And I know that if I plug in 0 for u, I'd be at -3/9 or -1/3. And I know that I have an equilibrium over here at 3. So this must look like that. Now comes the calculus-y part. So everywhere up here above the axis, u prime is greater than 0, which means u is increasing, which means we move to the right. And everywhere down here, u prime is less than 0, which means u is decreasing, and we move to the left. So here, we're above the axis, we're getting pushed to the right. And over here, we're also above the axis. Oh, so we're getting pushed to the right. I don't know where my arrows were going there. We're above the axis, so we're getting pushed to the right. And everywhere in here, we're below the axis, so we're getting pushed to the left. So we have this really interesting thing happening with our unicorn population. 3 is an equilibrium, but it's unstable. All the values are moving away from 3. So if we were to start with exactly 3 unicorns, we would always have exactly 3 unicorns forever, because the derivative would tell me that u wasn't changing. If I start with 4 unicorns or 2 unicorns, we don't stay at 3. So if I get over this threshold of 3, then my unicorn population just keeps growing. If I dip down under 3, then my unicorn population gets pushed all the way in here to the negative. Now, I said weird stuff was happening at -9, so we can't get exactly to -9 because there isn't really a point there. However, if unicorns could exist and have negative numbers, then this would tell me that those unicorns, that population was getting closer and closer and closer to -9, but it couldn't ever become -9 exactly. Again, unicorns, I don't know. This time, since we did a couple graphically, I was thinking that we could do this one using the analytic approach, meaning we're going to use the local stability criterion. But if you want to graph this one, we can. Would anyone like me to graph it? Cool, I'm not seeing any takers on graphing, which is good because I really don't want to graph it. So the first thing that we do need to do is to figure out our equilibrium. I'm always starting off the same way. I'm setting this equal to 0. Well, looking at this, I can factor that e to the p out. And if I pull out e to the p, I'm left with p² minus 4. which means I've got two possible equilibria here, that P equals 2 or negative 2. Now you might be thinking, well, what about e to the P? Well, e to the P is never equal to 0. Doesn't matter what I put in there. I can approach 0, but I'm never actually equal to 0. This time, since we are talking about pandas, I am going to ignore that negative number. We're not going to have negative numbers of pandas. We're just going to focus on that P is equal to 2. So the next piece here is to figure out, is this point, is that equilibrium stable or unstable? To do that, I'm going to look at that P prime and I'm going to call that F, because what we need to do is find df dp. So to take this derivative, I don't know if it looks easier to do a product rule and then subtract another thing, or to factor it first and then do a product rule, but I'm going to go with the original way it was written. If I'm taking this derivative, I've got p squared times e to the p. I need a product rule. Derivative of p squared, I'll have 2p times e to the p, plus, we'll leave the p squared alone, times derivative of e to the p, but that's e to the p again, and then minus 4 times the derivative of e to the p, which is e to the p. And now I want to know, is this positive or negative at p equals 2? First of all, I'm going to choose to factor that e to the p out, because I know this piece will always be positive, no matter what we plug in. So then I'm left with 2p plus p squared minus 4. And if I look at that f prime at p equals 2, that would be e to the 2. 2 times 2 will give me 4, plus another 4 minus a 4. Well, that right there is telling me that my derivative is positive. If the derivative of our p prime works out to be positive, then I know p equals 2 is unstable. Well, let's think about what that means in the context of this question. Well, if p equals 2 is unstable, and my only equilibria here were at 2 and negative 2, then p equals 2 being unstable means the numbers are moving away from p equals 2. Well, if it's unstable and I'm starting with 12, and 12 is something above p equals 2, then that means it's going to keep getting bigger and bigger and bigger and bigger and bigger, because it has to be moving away from p equals 2. So even without graphing this, I can kind of think about like fake number line-ish. If that's 2 and it's unstable, then I know that's what the arrows look like, right around 2. 12 is out here and it's going to get pushed bigger and bigger and bigger. So what's going to happen to my panda population after a really long time? It will grow infinitely large. Probably not good for the Earth. If we had an infinite number of pandas running around, I don't think there'd be space for the rest of us. Okay, so option 1, we're going to find the equilibria. We're going to sketch what this looks like. We're going to do that phase plane thing. The problem is, sometimes I look at an equation and I'm like, I don't know how to sketch that. Finding the equilibria I can do. I can set this equal to 0. I know that both of these have a p term in them. I can factor that p out. And if I factor p out here, that's really like a p to the 3/3. So when I pull it out, I'd be left with p to the 2/3 minus 2. So that's going to tell me that p equals 0. And this one, if p to the 2/3 is equal to 2, then I can cube both sides, and I'd have p squared is equal to 2 cubed, or 8, and then I can take the square root. So p would equal to the square root of 8. So I have my two equilibria, and now I have an option. Either I can sketch what this graph looks like, or we can use the local stability criterion, sometimes referred to as the analytic method. And what that means is getting back to the idea of, well, if I could sketch this, I don't know what that one looks like, I'll just pick a different one, right? If that's what my phase plane looked like, then everywhere that we're above the axis, we would be moving to the right. And everywhere that our derivative is below the axis, we'd be moving to the left. And what that means is an equilibrium where I'm moving to the left on one side and moving to the right on the other. Specifically, this unstable equilibrium, we have a positive slope of this derivative curve when we go through that point. When I'm at a stable equilibrium, we have a negative slope of the derivative curve. And that trend continues. Everywhere that I have an unstable equilibrium, we get a positive slope, stable equilibria, negative slope. Unstable equilibrium, positive slope, stable equilibrium, negative slope. So our book generalizes this into the local stability criterion and says, okay, we have this thing that looks like, insert your letter, y prime, x prime, n prime, whatever. In terms of that same variable, if I call this derivative function f of p, then when we look at how f is changing with respect to p not b, if it's greater than 0, oh, and notation-wise, sometimes the book uses a little asterisk or a star here to indicate that that's an equilibrium. So if f prime at my equilibrium is greater than 0, then that's an unstable equilibrium. But if f prime for my equilibrium is less than 0, then it's stable. Turns out when, that's an f. Turns out when f prime is equal to 0, that's usually when we get that weirdness of like that first problem that was semi-stable, where it was kind of stable from one side but unstable from the other side. Most of the problems we're getting asked about are going to fall into one of these two categories. So let's see what's happening in this problem. So we've got that p prime. So if I call that some function f and we take its derivative, so we're kind of now into the second derivative territory. But if I take the derivative, I'm going to get 5/3 p to the 2/3 minus 2. And what we want to know is at 0 and square root of 8, when we plug those in here, do we get a positive number or a negative number? So let's start with, if I look at f prime of 0, 0 to some power is still 0. 0 minus 2, I'm at negative 2, which means that is less than 0 overall, and it's stable. Then if I look at f prime of the square root of 8, that would look like 5/3 of the square root of 8 to the 2/3 minus 2. Well, square root of 8 is squared. Now I'm at 8. If I take the cube root of that, I'm at 2. So this is the same as 5/3 times 2 minus 2. It's a Monday. I'm not feeling great about fractions, but if I'm going to subtract stuff, I need a common denominator. So that's going to need a times 3 over 3. So I'm looking at 10 thirds minus 6 thirds. So overall, I think that's a positive 4 thirds. That is greater than 0, and it's unstable. So back to the question at hand, if I start with 50 piggies, how many will there be after a really long time? Well, now we're in exactly the same situation as we were with the other problem, in that I'm greater than square root of 8, and square root of 8 is unstable. So that means we're going to get pushed to an infinite number of piggies. Suppose that I had actually said, what if we start with 1 piggy? Well, if I start with 1 piggy, 1 is between 0 and the square root of 8. So then I would look, is one of those two a stable equilibrium? Since 0 is stable, I know that if I start between 0 and the square root of 8, I'm going to tend toward the stable equilibrium. So if we started off with only 1 piggy, we would unfortunately head to that stable equilibrium of 0. So after a really long time, we would have no piggies. And what I want to do is to find A so that the equilibrium is stable. Well, the first thing we have to do is to figure out what the equilibrium is if we're going to figure out how to make it stable. Starting that same way on all of these problems, to find the equilibrium, I need to set that equal to 0. And when I set that equal to 0, I get 1 is equal to e to the negative ak. It's harder for me to think about it this way, so I'm going to rewrite this to say 1 is equal to 1 over e to the ak, because now I can see that if I were to multiply both sides, I would get e to the ak is equal to 1. I don't know why, it just, for me, I want to know that without the negative exponents. If we're finding the equilibria, we're looking for values of the number of koalas. So I've got to get that k out of the exponent. Using our pre-calc or 17a skills, I need to take the natural log. If I take the natural log of both sides, I'll end up with ak is equal to natural log of 1. Oh wait, what's the natural log of 1? That's right, I'll pretend everybody's shouted out 0. Well, that means that k equals 0 is the equilibria. I don't want that to be stable then. There is no mathematical reason why I don't want it to be stable. I just don't want all the koalas to die, right? Because if k is 0 is stable, then that means our koala population is going to die off. So I'm changing my problem because I would like the koalas to live. So we're going to find A so that the equilibrium is unstable. Again, there's no mathematical reason I'm doing that. I just don't want all the koalas to die. So how do we go about figuring stability? Now that we know what our equilibrium is, we have a choice. We either are going to think about this graphically, which is hard because I don't know the value of A. And maybe it's hard because maybe this isn't something I know how to graph or remember how to graph very well. But our other criteria for stability says I'm going to take that k prime and I'm going to think about that as a function of k. And then I'm going to find the derivative of this. Well, the derivative of 1 is 0. And here, my derivative is going to look like e to the negative ak times, chain rule says I'm going to multiply by negative a. So altogether, that says f prime is equal to ae to the negative ak. Well, if I want this to be unstable, that means that I need this to be greater than 0. E to some stuff is always greater than 0, so I don't have to worry about this piece. In order to make everything greater than 0, I need a to be greater than 0. So if a is a constant, and I need to find that constant so that the equilibrium is unstable, making a greater than 0 will satisfy that.